Hello everyone and welcome to my channel Network Bytes with Laksh. In this video, we are going to look at LSA 3, what is OSPF area and few other things. But before we jump on to that discussion, let's just see what we saw in the last video. So in the last video, we started with the discussion on link state advertisements. What are link state advertisements? For a router, an LSA is or a link state advertisement is an advertisement of the states of the links that it's connected with, and that is what is LSA, link state advertisements. And we have different types of LSAs. We have 8 types of LSAs: router LSA, network LSA, summary LSA, summary ASBR LSA, autonomous system external LSA, multicast OSPF LSA, no not so stubby area LSA, and external attribute LSA for BGP. There are 8 types of LSAs, and in the last video we saw about LSA number 1 and LSA number 2. So we know that LSA number 1 or router LSA is basically generated by all the routers in an OSPF network, right? And we discussed what are the contents inside the LSA. That means for R1 in this case, when it generates an LSA, it talks about the links that it's connected with, right? That is the loopback addresses and the serial interface that it's connected with. What is the LSA age, and what is the checksum, and how many networks or links that it's connected with, what is the sequence number of the LSAs. We also discussed how important is the age and the sequence number of LSA in order to avoid the loops, right? We saw that. And then we discussed the database information that is present inside LSA number 1, right? So we discussed when we do a show IP OSPF database router, because that's the name of type 1 LSA, router LSA, we will see that the LSA shows us the information of the links that the router is connected with, the network running on those links, cost of R1 to reach those links, and the neighbor that is reachable over those links is also available, and the IP address of the particular router which is generating the LSA. We can all see those information in LSA1 database. Then we discussed about LSA number 2. First of all, we discussed what was the need of having LSA number 2. The reason was, if there is one single OSPF network, we will have increase in LSA1 message, and the size of the LSAs will also increase. The number of adjacencies that we will have to create with all the routers in the network will also increase, and flooding of the same database to all the routers will also increase. In order to reduce this, we created the concept of DR and BDR. We understood the concept of DR and BDR with classroom analogy, where the class monitors and the assistant class monitor is called as the DR and BDR, and the rest of the class is called as the DR other routers, right? And we discussed how the DR and BDR are basically elected. So in an OSPF network, every time an election takes place for a DR and BDR, a BDR is first elected. Since there is no DR, BDR takes over the role of DR, and then again BDR election takes place. The DR is always listening to the multicast address of 224.0.0.5 and 224.0.0.6. So if all non-DR routers, if they want to send a message, OSPF message, they will send at 224.0.0.6, and that will reach to DR only. When DR responds to any update, it will send the response at 224.0.0.5. We saw how the database is created using LSA number 2, right? We discussed all that, and in today's class we'll start our discussion on LSA number 3. So LSA number 3 and OSPF areas have something in common. We'll discuss that in some time, but let's just understand what is an OSPF area. But before we understand the area, let's try to understand, if there is one big OSPF network of routers, what are the problems that can create, right? So one major problem that would be created is the LSA flooding. Just imagine that this is one big OSPF network, and imagine if the link between R5 and R6 goes down, R5 and R6 both, they will generate their LSA1. router LSA. That means there is some change in the network. We saw that in our previous video that whenever there is a change in the network, the routers produce an LSA 1, right? So now the link between R5 and R6 goes down. Both of them will generate LSA 1, and that LSA 1 will be flooded across the whole OSPF network. And just imagine this poor router R1. He will receive all the LSAs that are created, not created, that are flooded by all the routers. And eventually, just imagine the amount of processing that it needs to do just because one link between R5 and R6 went down, right? So LSA flooding increases. Then the link between R5 and R6 goes down. Both of them will try to reach each other through an alternate route. And for them to reach with an alternate route is through R14, which they will eventually find out in couple of seconds. But then the moment they release an LSA, it floods across the network and it reaches R1, right? So now R5 and R6, they tell they lost the connectivity, right? And R1 in its database will also have to update that R5 and R6 now have lost the connectivity between the network, between the link between them, right? So now R1 has to update that, right? And then it needs to acknowledge. So that acknowledgement has to come back to R5 and R6. Now just think, every time there is a link failure and the link comes back up between R5 and R6, how many LSAs will be generated? And this poor router R1, how many times he has to do that work? So your database again is unstable. The amount of LSAs is flooded. The convergence takes time, right? R1 does not need to know what is going on between R5 and R6, to be very honest. It does not need to know. Even though, because it's one huge network, that information goes to R1 and R1 has to respond. And because all the LSAs that are generated and that are flooded has to be processed, and hence all the routers CPU processing is also taken, their memory is consumed. So this is one problem with one having a single OSPF network. And in order to avoid this, right, we came up with different OSPF areas. So as you can see in this diagram, that the network is divided into three circular areas. And now what is an area? Area, you can imagine it as a small region of a big network, right? So here I have mentioned that there are three circular areas, and the good thing about the area is that the LSAs that are generated inside a single area stays in the area. It's like what happens in Vegas stays in Vegas. That's how the LSAs are treated. Whatever LSAs are generated in a particular area stays in the area. They are not sent across other areas. So now just imagine the link between R5 and R6 goes down, right? LSAs are generated, but those LSAs will never cross their area. They will not even reach R11, R16, R13, let alone they reach R1. So what happens? R1 is completely undisturbed. R1 is running peacefully. All the other routers who are not part of R5 and R6 area are working peacefully. Their database is untouched. They are unbothered by the LSAs that are generated by R5 and R6. And R5 and R6, whenever their link goes down or goes or comes back up, they will disturb only the routers which are in their area. Other routers will be unbothered. They will not even care what's going on, right? So that's the effect of areas. And with that, what is happening? We are reducing the number of LSAs that are sent across the network. The edge routers here, R5 is one of the edge router, R1 is one of the edge routers. They both are unaware of what's going on in their area, right? Their database is same because the database is maintained only for the area that they belong to. CPU processing of the routers is decreased because they now do not have to process all the LSAs. So this are few importance of why the OSPF area is needed. Now let's discuss something more on areas. Now there are two type of areas. One is a backbone area, the other is a non-backbone area. The backbone area is called as the area 0, and any other numbered area, be it 1, 2, and it can go up to million numbers. They are non-backbone areas, right? Then there are different type of routers also. So the routers belonging to the backbone area here in this diagram, R1, R2, R3, and R4, they belong to the backbone area, and they are called as backbone routers. Okay, and R3 and R4, they are called as area border routers, or ABR. The condition for a router to become an ABR is that one interface of the router should be a part of backbone area, and another interface should be a part of a non-backbone area. Then only a particular router can become an ABR. So R3's one interface is part of area 0, the other interface is part of area number 2, and hence R3 is an ABR. The same goes for R4. So R3 and R4 are area border routers, or in short, ABRs. R5, R7, R9, R8, R6, R10, they all are internal routers. Even R1 and R2 are internal routers, meaning that all their interfaces are part of a single area. So if you see R5, R7, and R9, all their interfaces are part of area number 2 only. The same for R6, R8, and R10, all their interface are part of area number 1. And for R1 and R2, all their interface is part of area number 0. Right? Now, we know that OSPF is a link state protocol. Right? We have been discussing this. For the past 2 videos. Right? Link state protocol. Now, as I said in the previous diagram, that the LSAs that are generated in a single area do not cross other areas, right? So the LSA that is generated inside area number 2 never go to area number 0. The LSAs that are generated in area number 1 will never go to area 0. And the same, the LSAs generated in area 0 will never go to area 1 or area 2. So the question comes is, how will, let's say example, how will R7 know about R8? How will R7 reach R8? That is where the ABRs R4 and R3 come, right? So R4 says that if you want to reach R8, R4 says if you want to reach R8, you send the data to me, and he sends this information across his area. R4 says if you want to reach R8, since I am a part of area number 1, right, I know how to reach R8, and if you guys want to reach R8, send your data to me and I will send it to R8, right? So R4 sends this update to R3. R3 being in the same area as area 0, and R4's one interface is also part of area 0, this update also reaches R3. R3 now knows how to reach R8, that is via R4. It passes on this information to R7, but it says if you want to reach R8, you send the data to me, I will forward it, right? So now R7 knows how to reach R8. When R7 tries to send the data to R8, he will send the data to R3 thinking that R3 will forward the data, and that is what R3 had promised. I will send the data to R8, you just forward the data to me, right? So R3 now knows how to reach R8 because R4 said if you want to send the data to R8, send it to me. So R3 sends the data to R4. Now R4, since it's a part of area number 1 all as well, it will send the data to R8, and hence R8 and R7 can communicate this way, right? Now, how does R4 share this update, or R3 share this update to each routers or in other areas? We'll understand that in some time. Now, as we were discussing about the communication, we saw that the LSAs that are generated here remain in the same area. So what is happening? Inside the same area, the OSPF is working as a link state protocol, wherein R7, R5, R9, R3, they all know about each other's links and their states, and their database is same. They know about each other's database, they have their own topology. But R7 is completely dependent on R3 to reach any router outside its area. It's completely dependent on R3. So whatever information R3 shares, that is what R7 takes as true, right? So R3, being the ABR, is responsible to share those information, and hence OSPF for an inter area communication behaves like a distance vector protocol, just like EIGRP. In EIGRP, we know that a particular router, for example, let's say R1, R2, R3, and this is X network. R1 completely depends on R2 to reach X network. R2 is completely dependent on R3 to reach X network, right? In EIGRP. This is what distance vector means. And similarly in OSPF also, your inter area communication is a distance vector OSPF, and intra area communication is link state OSPF. Right? This is another, like, an interview question that I have been asked a lot of time, that how does OSPF behaves? It's a link state protocol or it's a distance vector protocol. So I say intra area OSPF is always link state, but inter area OSPF is always distance vector. Right. Now, as I had mentioned that when R8, right, R8 shares its LSA, right, it reaches R4. Since R4 is a part of area number 1 and is also a part of area number 0, it is an ABR. And R4 tells other routers that if you need to reach R8, you send the data to me. And it shares this information using the LSA number 3, that is the summary LSA, LSA number 3. And whenever it becomes an ABR, whenever the two routers, be it either R3 or R4, whenever they become an ABR, and again I'm emphasizing that if a particular router wants to become an ABR, one interface should be part of area number 0 and another interface should be a part of area number 1. At least one interface should be a part of area 0 and at least one interface should be a part of area number 1, and hence they will become ABRs, right? So whenever a router become an ABR, it generates an LSA number 1. It generates an LSA number 1 where it sets the B bit. This is the boundary router bit. Boundary router bit to 1, and which means that it is telling that it has now become the ABR. So whenever it generates an LSA 3, that means you need to send the data to R4 in order to reach the networks that are present inside LSA number 3. We'll talk about what is present inside LSA number 3 in just a while. But just understand, whenever a particular router becomes an ABR, it generates an LSA number 1 where it will set the B bit or the boundary router bit to 1, which indicates that it has become an ABR, and now it is responsible for generating LSA number 3 and letting you know how to reach other networks, right? So when, let's say, when R4 generates LSA number 3, it will talk about, let's say it talks about R8's network. It says R8's network is 8.8.8.8. its address mask is 32. I am the advertising router, that is 4.4.4.4, which is R4's router ID, right? And my cost to reach R8 is 2. and this is what it shares to R2, R1, and R3. Right now, let's take the example of R1. R1 receives this information, right? R1 receives this information about R8's network, that is 8.8.8.8 via R4. So now R1 knows how to reach R8 via R4. So now R1 will calculate its cost to reach R4, right? That is one, we know that for fast Ethernet, the cost is 1, right? So R1's cost to reach R2 is 1, R2's cost to reach R4 is 1, and R4 has mentioned that its cost to reach 8 network is 2. So that means 2 plus 2 equals 4, and now R1 knows its cost to reach R8 is 4, right? Similarly, when this LSA number 3 that is generated by R4 reaches R3, it knows that R4's cost to reach 8888 or R8 is 2. It will then calculate its cost to reach R4, which basically is 3. So R3's cost to reach R8 is 3 plus 2, that makes it 5. Right. So now R3 will generate its own LSA. It says, if you want to reach R8, you send the data to me and my cost to reach R8 is 5. Now, when R7 wants to calculate its cost to reach R8, it will just add the cost to reach R3, right, which is 1 plus 1, that is 2. And it already knows R3's cost to reach the 8 network is 5. So the total cost of R7 to reach R8 is 7. This is how all the routers in different area calculate their metric through LSA number 3. So let's do a small practical on this now. So here I have 5 routers, R1, R2, R3, and R4. You can see the interface IPs. On R1, I have fast Ethernet 0/0 and loopback 1 with IP address 12.0.0.1 and 1.1.1.1 respectively. I have run the OSPF already on all these routers. So on R1, it's router OSPF 1, network 0.0.0, and area 10. So area 10. If you had noticed in my earlier videos, I always mention the area. So that means 2 routers are part of the same area. And this is another condition. If 2 routers have to become adjacent, they need to be part of the same area. That is why I always mention area in the end of a network command. And the network command I've used is 0.0.0. That means I'm advertising all the interfaces, and I'm sending OSPF through OSPF hello messages through all the interfaces. You can see loopback 1 and fast Ethernet 0/0. They are part of area number 10. Their address and mask and their costs. Similar router configuration and IP configuration you can find on R2. You can pause the video just to see what is the IP address that I have configured if you are following, right? And on R3, you can see the IP addresses that I've configured. The OSPF that I've configured on R3 is a bit different, where I have configured the 23 network which is facing R2 to be a part of area number 10, and 34 network which is facing R4 to be a part of area number 0. So I have entered 2 different network commands, right? And you can see loopback 1 and fast Ethernet 0/0 are part of area 0, and fast Ethernet 0/1 is part of area number 10. And you can see their IP addresses and mask and the cost. The same goes for R4 and R5. Okay. Now, if I do show IP protocols, we can see that it says the router ID is 3333 and it is an area border router. We know that it's an area border router, right? And how do other routers know it's an area border router? We know that it generates an LSA 1 whenever it becomes an area border router, right? Now R3 is an area border router. So how will I find out if which router is an area border router as an admin, right? I was not there when the routers were being deployed. I just came in. How do I find out which router is an area border router? And to find out, the command is show IP OSPF border routers. We can see on R1, when I did this command, when I run this command, it shows that the router with the router ID 3333 is the area border router, and R1's cost to reach 3333 is 2 via 12002, which basically is R2's interface, right? And it's an ABR, and it is a part of area number 10, right? We can see this. So as I mentioned, whenever a particular router becomes an ABR, it will generate an LSA and will set the B bit or the boundary router bit to 1. So let's check that. And on R4, right, if we do the same thing, show IP OSPF border routers, right, we will not see this, right? We can see that R3 is the border router. We know that. So what I'm going to do is, let me first enable Wireshark on this interface to show you the LSAs that it generates. On R3, what I'm going to do is, I will shut down the interface, loopback interface and 0/0 interface on R3, right? When I do so, configuration terminal, interface loopback 1, shut. Obviously, the OSPF will come down. Interface fast internet 0/0, shut. Okay. Now on R4, if I do show IP OSPF border routers, it still knows, right? It will take some time to erase this particular information. Let's check on R1. Does it know which is an area border router? No. So obviously on R4 also this change would have occurred now, right? So it also does not know. It does not know which an area border is, which is an area border router. On R3, let's check show IP OSPF show IP protocols. We can see now there is no mention of area border router, that this router is an area border router. No, it does not say anything. Right. Now let me open Wireshark and enable the two interfaces again. Configuration terminal, interface loopback 1, no shut, then interface fast internet 0/0, no shut. Now we can see that R3, whose interface IP is 23.0.0.3, has generated an LSA. You can see it generated an LSA update, right? And if you open, it has generated an LSA number 1. And inside the LSA number 1, right, we can see that it has set the B bit, border bit or area border router bit to 1. Now this is how it is telling everybody that it has now become the ABR, and since it is the ABR, it will generate LSA number 3, right? So whatever networks that you want to reach to, right, you send the data to me, right? I am the area border router. I will take you to the network that is outside your area. Now let's go back to our original diagram. Let's go back on R1 and check show IP OSPF border routers. Now R1 knows which is the ABR, right? So this is how the routers know about the area border router. Whenever an router becomes an ABR, it generates an LSA. In that, it sets the B bit or the area border router bit to 1. Now, let's check R1's database. Show IP OSPF database. Right. We can see that R1 knows about the LSA number 1, which I said is basically generated by all the routers in the same area. R1 has generated, R2 has generated, R3 has generated. You can see two LSA 2s generated, 12002 and 23003. If you see, this LSA number 2 has been generated for the links between R1 and R2 and the other for R2 and R3. We know that these are fast Ethernet interfaces, and OSPF considers fast Ethernet interface as a broadcast interface. So obviously, between R1 and R2, there will be a DR and BDR election. The DR will generate an LSA number 2, and in this case, R2 is the DR, and hence it has generated the LSA number 2. Between the links of R2 and R3, R3 becomes the DR, right? And hence R3 has generated the LSA number 2. We can see that. But since we are not looking into LSA and LSA number 2 in today's class, we have already seen that in the previous video. We'll jump to the LSA number 3. That is generated by R3, and that is what you see in the advertising router. Okay. It says that it has generated LSA number 3 in the area number 10. And in the area number 10, you can see the link IDs of the network that are part of area number 10. 3333, which basically is R3's loopback address, is part of area number 0. I had shown you the configuration. Loopback is part of area number 0. This is R4's loopback. This is R5. This is the link between R3 and R4, and this is the link between R4 and R5. All of them are part of area number 0, and R3 generated an LSA number 3 talking about them, right? So all the routers know if they want to reach R1, we are checking on R1, right? R1 knows if it wants to reach any of these links, it needs to send the data to R3. That is the advertising router. That is the basically ABR, and it knows that to reach the ABR, its cost is 2, right? And what is 3333's cost to reach R5? In this case, R5's loopback address. So show IP OSPF database, right? Let's check the R5. Show IP OSPF database summary link for summary database for 5.5.5.5. Right. It says that to reach 5.5.5.5, I am the advertising router, and my cost to reach the link 5.5.5.5 is 3. So 3 plus R1's cost to reach R3 is 2, right? So 2 plus 3, that makes it 5. 3 plus 2 is 5, and R1's cost to reach R5, total cost, is show IP route OSPF. We can see that R1's cost to reach R5 is 5. And similarly, R5 would have also calculated. R5, when it checks its show IP OSPF database, it knows that to reach 1111, it needs to reach 3333, right? And 3333 is the advertising router for LSA number 3. So obviously, it needs to be an ABR. And what is R5's cost to reach the ABR? That is show IP OSPF border routers. That is 2. R5's cost to reach the border router is 2, right? And what is the border router's cost to reach link 1111? That is to be checked via show IP OSPF database summary. Okay, and since I have opened the whole summary, let's check for 1111, right? Link ID 1111. The advertising router is 3, and the advertising router's cost to reach 1111 is 3. So that means 3 plus 2, that is R5's cost to reach 3333, right? And in total, R5's cost to reach R1 would be 5. Show IP OS, sorry. So show IP route OSPF. R5's cost to reach 1111 is 5. And this is how inter-area communication takes place. And this is how LSA 3s are generated and how they share the information of each network uh, to their internal routers. This is just the part 1 of LSA number 3. In the next video, we'll check about summarization and filtering with a bit of a complex network, not as easy as this. We'll check a bit complex network and how summarization and filtering is done. We'll see that. Till then, please do like, share, and subscribe, and have a great day. Bye bye.